Hello everyone, welcome back. Now as a note, a fun kind of note, I currently have a ice pack attached to my computer with a rubber band. It's because my screen is dying. So if I ever start randomly drawing in the wrong place, it's because my screen died and I can't actually see what I'm drawing on, but I'll just do my best from memory. Hopefully that won't happen, but if it does, now you know why. I'm not crazy. I'll go back and edit it, but I might leave it there for the very first time just to let you see the hilarity. So what we're talking about this time, we're talking about position vectors and force vectors. Like, okay, we've been talking about vectors all this time. Is this entire class vectors? It is. It really is. It's all vectors. Everything. That's it. So position vectors and force vectors. You're like, well, is there really a difference between a force vector and a position vector? There's not. I mean, the way you solve for them is pretty much the same. The big difference with a position vector is you might have to realize that it's not always going to start at the origin. It might be starting at some random place in space. You have to figure out what the vector is from that. But the way we work with them is very much the same. So we're going to learn how to represent a position vector in Cartesian coordinate form from the given geometry and figure out how to direct a force along the line of the position vector. Very helpful. So let's jump into some applications first, because we got to figure out why this is relevant. The big thing for us is that, we have big things like this ship, and it's attached to the pier with a mooring rope. Now we can figure out the position vector of that mooring rope. And what we realize is that the forces that are coming from the ship that are keeping it in place, they have only one way to go. They can only go down the rope. They can't just float magically through space. They have to go along the rope. So the position vector for the rope and the force vector have the same direction, just different magnitudes and different units. Now, why do we want to know this? Well, we need to know how hard are we pulling, well, one, on that pylon, and two, on the boat. Is it going to break? Is the thing on the boat okay? Is the rope going to be okay? Is it going to snap? There's a whole lot of things that we need to understand in order to understand what's going on here and to be able to keep that boat stable, to keep it static. Statics. The thing is, maybe we have some sort of awning. One of those big awnings you see like in New York City or in big cities. Greensboro, not such a big city. It's held up with 3 chains. Well, we need to know the forces in those chains because we need to know, is this going to stay stationary? Or if I start pushing on it a little bit, is it going to start moving, swinging, bending in such a way that it's going to die? We don't really care about bending in this class because it is statics. Nothing moves, nothing bends. Same thing with dynamics. If you get to my solid mechanics class, they'd be like, oh yes, we care about that. That's super important. And so why do we care about position vector? Well, we care about position vector because we know where the ends of the chain are. And since we know where the ends of the chain are, we can tell what direction the force is directed. Because overall, it's directed along that chain. Now, obviously, it's made of little links. If you look at it at a very small scale, it's all kinds of craziness. But overall, the force is directed through that chain. So if we know the position vector, then we know the direction of the force. And then we can solve for its magnitude to figure out, is it going to be stable? Is it going to stay in place? So let's try this out. How do we get a position vector? It's not actually all that hard. Usually you'll know the beginning and the end point. It won't always be on the origin. The origin is 0. So if it's on the origin, it just makes things simpler. The way it usually is, it's just the relative position from any particular point. So here's A, here's B. And what I need to know is I need to know where A and B are in space. So I'll have an X, Y, and Z component of their position from the origin. And if I want to find the position vector from A to B, then I subtract the end from the beginning. Subtract the beginning from the end. So it's always B minus A. If I'm going A to B, I take B and subtract A. Just trying to make sure that the arrow points in the right direction. If you're unsure if you did it right, just look at this. You can see that this position vector is going in the positive Y and Z direction. If you do it wrong, it'll be going in the negative Y and Z direction. And you'll know, okay, I got the wrong sign. I just need to multiply everything by -1. And that'll work. So here is our position vector. If we want to, we can then write this in Cartesian coordinates. So this is a position vector directed from A to B, and this is how it's written, okay? First one is start, second one is end. Okay? First one start, second one end. End goes to the first here. Start goes second. And as it says, always subtract the tail coordinate, that's the tail, from the tip coordinates. That's just the best way to do it. Okay, we'll go ahead and stop here, and next time we'll talk about how we're going to use this to help ourselves when it comes to the force vectors. Okay, hope you enjoyed this. I'll see all of you later. Bye-bye.